Welcome to the Explainer, everyone. Class is officially in session, and today we are heading straight to orbit. I am absolutely thrilled to be your instructor for this masterclass, taking you on a journey literally hundreds of miles above the Earth's surface. We're going to build a comprehensive step-by-step guide to satellites. We'll demystify these incredible machines, break down exactly how they survive in the brutal environment of space, and figure out why they are, honestly, completely essential to our modern way of life.
So let's dive right into this with a number that is just kind of hard to wrap your head around. 9,500. Take a second and just let the sheer magnitude of that sink in. That represents the staggering amount of man-made satellites orbiting the Earth right this very moment. It's effectively this massive, invisible, high-tech highway system, and it's operating silently right above our heads.
And to really ground our lesson today in some serious real-world space expertise, we're drawing directly from the ultimate classroom, the International Space Station. Nick Hague, a NASA astronaut currently aboard the ISS, sets the stage perfectly for us. Quote, "Hi, I'm Nick Hague, NASA astronaut aboard the International Space Station, the largest of over 9,500 man-made satellites orbiting the Earth." Hearing that directly from an astronaut living inside the largest satellite ever built? Yeah, that's the perfect jumping-off point for what we're about to unpack. Here is our syllabus for today's Explainer. 1. Welcome to orbit. 2. The jobs of a satellite. 3. Step-by-step satellite anatomy. 4. Payloads, the mission hardware. And finally, 5. Case study, the ISS. Let's get to it.
Section 1. Welcome to orbit. You know, when we picture a satellite, it's really easy to just imagine a generic metal box. But the reality is, these machines are incredibly diverse.
Section 2. The jobs of a satellite. Why exactly do we spend billions of dollars to put these machines up there? Well, because they solve massive Earthbound problems.
It's fascinating how we categorize these massive jobs. First up, we have communication. That's the invisible tether connecting our data, our media, telephone transmissions all across the globe. Then there's navigation, which gives us the exact signals we need to pinpoint locations. Yes, this is exactly how your phone's GPS knows where you are down to the meter. But I really want to highlight this third category right here, Earth observations. This is absolutely critical. Satellites monitor the Earth's surface to track weather patterns and assist in disaster management. Think about it. When a massive hurricane forms over the ocean, or unpredictable wildfires start spreading across a coast, these observation satellites are the essential tools giving us the immediate high-altitude data we need to respond and save lives. And finally, science, where super-sensitive sensors collect crucial data to help us study deep space.
Section 3. Step-by-step satellite anatomy. Okay, we know what they do, but how do they actually pull it off?
Let's literally strip a satellite down to the bolts. The crucial point here is understanding how these systems rely on each other in sequence. Step 1. Every satellite needs a power source, which is usually vast arrays of solar panels. This is the lifeblood. It provides the energy needed to run all the electrical systems, because without power, you basically just have a very expensive piece of space junk. That power flows to Step 2, the communication system. Since every single satellite's job is to either collect or relay data, they absolutely must have a comm system to talk to Earth or other spacecraft. But here's the kicker. That comm system, totally useless if the antenna is pointing off into deep space instead of down at us. Which leads us to Step 3, attitude control, the system required to correctly orient the satellite and its delicate sensors.
Let's elaborate on that third step for a second, because attitude control is an absolute masterpiece of engineering. In the frictionless vacuum of space, you can't exactly just turn a steering wheel, right? Instead, they use specific mechanisms like small, precisely timed thrusters, or these rapidly spinning gyroscopes. Their sole vital purpose is to keep the satellite pointed in the exact right direction at all times. They are the physical tools perfectly aligning everything in the vacuum of space, making sure solar panels face the sun and antennas face the Earth to keep that vital connection alive.
Section 4. Payloads, the mission hardware. So we've got power, comms, and attitude control. Those are pretty standard across almost all 9,500 satellites.
So what actually makes each mission unique? It all comes down to the payload. A payload is defined as the onboard hardware that the satellite uses to perform its designed function. Simply put, this is the entire reason the thing was launched in the first place. Everything else we just went over, the solar panels, the thrusters, the gyros, they are essentially just the delivery truck and life support system designed to keep this specific payload working in the harshness of space.
And this brilliantly illustrates just how wildly varied these missions can be. Your payload could be deep space radiation sensors, out there measuring invisible, highly energetic hazards millions of miles away. Or it could be powerful telescopes, patiently staring outward to unlock the ancient secrets of the universe. Or, looking completely in the opposite direction, your payload might be thermal imaging cameras pointed straight back down at us. They constantly measure surface temperatures to help with that critical weather and disaster management we touched on earlier. The payload dictates the whole shebang.
Section 5. Case Study, the ISS. Let's bring all these concepts together by looking at the crown jewel of orbital engineering.
The International Space Station perfectly illustrates everything we've just learned, mainly because it acts like multiple satellites rolled into one massive structure. On one hand, it's an orbiting laboratory, a highly controlled space where humans actually perform cutting-edge research in a pure microgravity environment. But on the other hand, it simultaneously operates as a state-of-the-art Earth observation platform. It's equipped with precise windows and advanced sensors strictly for watching the Earth below. It's got massive solar arrays for power, complex comms for ground control, advanced gyros for attitude control, and its payload is basically a constantly rotating suite of scientific instruments. Oh, and of course the astronauts themselves.
Well, that brings us to the end of our orbital masterclass. But before we go, I want to leave you with this one final provocative thought. What would our day actually look like without these 9,500 machines functioning silently above us? Imagine it. No precise navigation, no global weather tracking, a massive breakdown in worldwide communication. It is incredibly humbling to realize just how deeply our daily lives are tethered to these feats of engineering floating in the dark. Thank you so much for joining me today to explore the anatomy of satellites. Keep looking up, and I'll see you in the next explainer.